I realized I should have given the title Elliptic Algebras, because there are a huge number of algebras that deserve the title Elliptic Algebras. I don't have a definition of elliptic algebras, but for example, in response to the question you just asked Natalia, are there cubic Sklyanin algebras? Yes, there are. There are algebras generated by two elements subject to two homogeneous cubic relations that behave exactly the same way as the three-dimensional Sklyanin algebras that Natalia was talking about. And those should be called elliptic algebras too. But these are not belonging to the family of elliptic algebras that Fagan and Odesky defined. I should say that any new things I say, joint work with Alex Chirvasitu and Kanda. Both Chirvasitu and Kanda came to the University of Washington for their postdocs, and I was very lucky because they're very hardworking young guys, nothing else going on in their life except mathematics. These emails are going back and forth at 2 a.m., 5 a.m. Anyway, yeah, I've learned a lot over the last 4 or 5 years working with these guys. Oh, thanks for inviting me to speak. Thanks for inviting me to this conference. It's been fun to meet all these people, none of whom I've met before, but lots of your names I recognize. And you do very different kinds of non-commutative algebra than me, but I think there's some room for interaction and overlap. So in 1989, Fagan and Odesky defined a family of algebras, and I'm going to denote them first as follows. Well, they're going to be algebras over the complex numbers, and I'm going to say informally that they are deformations of polynomial rings. Now, I've noticed that the word deformation and degenerate are often used somewhat informally, but one can be absolutely precise here in saying that what one has is one has some algebraic variety parametrizing a family of algebras, and it's a flat family of algebras. That's what I mean by that. And flatness, it's a technical condition, but it means basically that things behave well in that family. For example, if you have a family of graded algebras, it will be flat if the dimensions of the homogeneous components are the same for all the algebras as you vary the algebra. Okay, so these depend on some data. A pair n bigger than k bigger than or equal to 1 of relatively prime integers, a point tau in the upper half plane, imaginary part of z positive, and a point eta, be any point in C, and I'm going to denote it by Q in K eta tau. And this is going to be denoted by n elements, and my indices here are going to be taken from the cyclic group of size n modulo some homogeneous quadratic relations. I won't write the relations down yet, but when I say these are deformations of polynomial rings, when eta is 0, then, well, maybe I should have just said that Q n k 0 tau. This is a polynomial ring n-1 variables, on n variables, sorry. And also another case when k is 1, ditto. You also get a polynomial ring. Okay, so let's fix n and k and tau and just vary eta. Then we get a family of algebras parameterized by the complex numbers. Yep. and those all have the same size as the polynomial ring in n variables. Let me say that Q31 here, this is sometimes called the three-dimensional Sklyanin algebra. And these, as Natalia said, were found first by Artin and Shelter, I think around 1986. Q41, this is called the four-dimensional Sklyanin algebra, and that was found by Sklyanin around 1982. Sklyanin didn't know Artin and Shelter, and Artin and Shelter didn't know Sklyanin. These were completely separate developments. So, as I said, that's what Natalia was talking about. But when she mentioned Sklyanin, Sklyanin had nothing to do with that. He had to do with this one here. And these are quite well understood. This one, due to the work of Artin, Tate, and Vandenberg, quite a good team to have on your side. And this is quite well understood too, at least as well understood as that, due to the work of many people, some of whom Natalia. Once you get beyond four generators, very, very little is known. Fagan and Odesky have a number of papers about these, but they don't have a lot of proofs. They make a lot of assertions about these algebras, fascinating properties, but you look for the proofs and they're just not there. And some of these assertions are not correct. They're very close to being correct, but as we know in mathematics, everything's balanced on a razor's edge. And without that proof, you don't have it. But their papers are very good as a source of inspiration. And a lot of what I've been doing with Chirvasitu and Kanda is simply trying to prove things that Fagan and Odesky say. Okay, now I have to introduce some notation associated to this data. So lambda sub tau is going to be the lattice inside the complex numbers generated by 1 and tau. And so C mod this, I'm going to call this E sub tau. This is a compact Riemann surface of genus 1. So it's an algebraic variety. And as an algebraic variety, it is an elliptic curve. Yeah. Okay, so I want to say a little bit about these homogeneous relations. First of all, there are n squared of these relations. Now think about the polynomial ring for a minute. Polynomial ring on n variables has only n choose 2 relations. N choose 2 relations, which is a lot less than n squared. So even to show that these things are polynomial rings, you've got to take these n squared relations and show they span a vector space of dimension exactly n choose 2. That's not too hard in these cases. But in general, what I said is I've got a flat family. So all these algebras have the same dimensions in their homogeneous components as the polynomial ring. So the first thing you've got to do before you can assert that this is a flat family is you've got to prove that these n squared relations span a vector space of dimension n choose 2. And that is extremely difficult. And we can't do that for all etas. We can't do that. Now, eta here gives us a point. Take the coset here, that's the point I'm going to call that C on this elliptic curve. Now, if this, okay, so an elliptic curve is an abelian group, S1 cross S1. Points on that elliptic curve have finite order in the sense of being in a group. If this has finite order, then it's very much more difficult to show that this space, and we can't do that for all of these points. Also to keep our feet on the ground, as let's let tau, this point in the upper half plane, go up the positive imaginary axis. And so this, and I'll explain how to make sense of this in a moment. We can take the limit of this algebra and get another algebra. And this thing here, okay, that's some algebra. Again, it has the same Hilbert series as the polynomial ring in 4 variables. So this is some algebra. It's got 2 elements, k and k prime in degree 1, such that their product is central. And so I can invert that product and take the degree 0 part, and this is UQSL2, which I know many people in the audience love. And I once loved too, but now I have greater love for these things. So these things are, okay, so going to be defined in terms of an R matrix, a solution to the quantum Yang-Baxter equation with spectral parameter. And as you know, these solutions to quantum Yang-Baxter come in 3 flavors: rational, trigonometric, elliptic. These guys are elliptic R matrices, defined in terms of elliptic R matrices. These are defined in terms of trigonometric R matrices. And you just take the R matrix that you use for this and you take the limit. This involves some theta functions, and then you get this thing. Okay, right, now I had to push a button, didn't I? Yes, tableau droit. Okay, great, I've got it. Right, so I want to write down, yeah, I'm going to write this as the tensor algebra on V modulo the image of a certain linear operator that depends on the input data. Right, so I want to define, well, it really depends on all the input data. That takes too long to write that out. This is going to be where V is vector space with basis. This set of generators that I just wrote down. So I have to tell you what this operator is. Every time I give this talk, I think, okay, am I going to try and be so clever as to show people I can remember this complicated formula without looking at my piece of paper? Most of the time I get it right, but not always. So, whoa, I think it's a minus Z. A minus 1 minus Z. Of course, you won't know if I've made a mistake or not. Yeah, close, but no cigar. All right, yeah. Okay, we're okay. Yes. So as you can see, you have this ij here is in Zn2. And so we're going to define this. Oh, what happens when I go back and forth like this? Do I have to change the camera? The image of this thing. Well, it's a complicated. Oh, I should say what these thetas are. Where theta alpha in Zn, a basis called just theta n of tau, which is a set of all holomorphic functions f such that plus 1 equals f of z, and f of z plus tau equals minus e of minus nz f of z. So these are theta functions. One can write down formulas for these thetas, but it's not always helpful to see those. Of course, at some stage you have to use the definition. Oh, what's e mean? Yeah, I write e of z for e to the 2 pi I. So here's some problems that arise. Oh, I should say, yeah, this R is Balavin's solution to the quantum Yang-Baxter equation that generalizes Baxter's original 2x2 solution. It's not obvious at first that this is Belavin's R matrix, because Belavin's R matrix is defined in a different way. There are theta functions in the definition, but his are different theta functions. They're theta functions with characteristics, as they're called. And I'm writing down this R matrix in terms of its action on these xi tensor xj. And if you know Belavin's paper, then you'll see an expression in there, W alpha of something or other, I alpha tensor I alpha inverse. These things are different than the EIs and the EJs, and I'll say a word about that. They come from the action of the Heisenberg group of order n cubed. But you have to do a little work to compare the two. But anyway, this was proved by, it was conjectured by Belavin. In the paper where he made this conjecture, he adds a footnote at the end where he says that he has a proof. And then I've seen proofs by Cherednik, I think. Chudnovsky and Chudnovsky, it takes too long to write their names down. And there's a nice exposition by Craig Tracy of this. But anyway, this plays an important role. Now, some difficulties with this. These theta functions here, they are quasi-periodic with respect to this lattice. So once you know they're zeros in a fundamental parallelogram for the lattice, then you know there's zeros everywhere. Now, it turns out that these thetas are kind of nice in terms of where they vanish. If you look at, if you take any point in here, then a value of R for which 0 here, you get a 0 here. So that's why we put in these terms up here to sort of cancel out that 0. We're trying to take this R, which is viewed first as a function of Z. It's not a holomorphic, an operator valued function of Z. It's not a holomorphic, it looks like it's got some poles, right? But this normalization factor out here is put in so that the poles vanish. The poles are, what do they call it? Removable singularities. So there is a bit of cleverness you can do to define R of Z for all Z and make it a holomorphic function everywhere defined. Yeah, the other thing, but anyway, the end torsion points always cause some problems because these things can vanish there. And end torsion points are corresponding, what we've got when we take the Q here. This Q is in C cross, a group. When Q is a root of unity, i.e. a torsion point in here, things are more difficult. And the same sort of phenomenon happens here. And in fact, there's a conjecture that this QNK eta tau is finite as a module, finitely generated over its center, finitely generated module over its center, if and only if the image of eta is a torsion point. Prove one implication, there are many cases where this is known to be true. What I want to do, I think, I really struggled with what to talk about to this audience. I thought at one stage it might be, is there an erase? Oh, there is. I thought at one stage it might be best to talk about just the 4-dimensional Sklyanin algebra, or even the 3-dimensional one. But anyway, I decided against that. I just want to show you some of the ingredients that go into understanding these algebras. And there's some really surprising things that happen. First thing I'm going to do is just introduce the Heisenberg group. Oh, thanks very much. So as an abstract group, central, and the commutator, the group commutator, S and T is this. So this is isomorphic to this group here. upper triangular matrices, unipotent upper triangular matrices. So it's of order n cubed, n, on holomorphic functions. Lots of actions, but the one relevant to us here, because we've fixed this integer n at the outset, is this, 1 over n tau. And this is an action of this group, and it turns out that this vector space I just defined, this is an irreducible representation of Hn under this action here, of dimension n, of course. Connection between Heisenberg groups and theta functions is ancient, so no surprise that this gets a look in. Yeah. So Fagan and Odesky observed that Hn acts as automorphisms of this Qnk. This acts on X alpha and T acts on X alpha in this way. Right. So it's not too difficult. Of course, again, if you're familiar with Balavin's of his elliptic R matrices, you will see in there that the action of Hn plays an important role in analyzing the candidate that he writes down for the R matrix. It turns out that, okay, so here I've written down the action on the degree 1 component. I've called V, right? It's defined, Q is defined as the tensor algebra on V, quotiented out by something. And it turns out that this Hn action on V, the degree 1 component, is isomorphic to space of theta functions, where I wrote down the action. Oh, well, I wrote down the action there. Now, this gives us an interesting thing, that the map, the holomorphic map from C to Pn-1, given by sending Z to these theta functions at Z, this descends E because of the quasi-periodicity properties of these things. If you change a point, and if you replace Z by Z plus some point in the lattice, you get a scalar multiple of this, so the same point in projective space. So this descends now to give us E, Pn-1. And we should really be a little more thoughtful about what this projective n-1 space is. What is it? It's really, given this description here, it's, now, how's this work? So this is, by definition, the lines in the dual vector space of that. So hyperplanes in theta n, hyperplanes in theta n. I can't even think now, sorry. But anyway, okay, I forget about that. But the point is, because of this is isomorphic to projective space of lines in V star, which is the degree 1 part of the algebra, or the dual of it. So we get from this setup a natural embedding of E inside the projective space dual of the degree 1 part of the algebra. So in Natalie's talk, she did mention in passing that you have this elliptic curve floating around. This is really where it comes from. Oh, yeah, and now once you've got E embedded inside this projective 1 space, there's a canonical line bundle on this projective space, usually denoted by yeah, this is Pn-1 because V was of dimension n. And we can now restrict this to E if we think of E sitting inside here. And this being a line bundle on Pn-1 restricts to a line bundle on E, and we can say exactly which one it is. Okay, what do we mean here? So I'm writing down a divisor here on E. So this point in the complex plane has an image in E, an image in E tau. So we take that point, add it to itself formally in the sense of divisors n times, and that's the divisor associated to this. So we also get from this data a distinguished line bundle on E. And that's going to play a role in some things we do later too. Okay, I want to pull a rabbit out of the hat now. An important aspect to understanding. Oh, I've got another blackboard there. Wow, I didn't even know that. Okay, given our relatively prime integers n and k, there exists unique integer g and integers n1 up to ng greater than or equal to 2, such that you have this equality, this negative continued fraction is equal to this. And it takes a long time to write out that negative continued fraction, so I'll just write it in this way. Okay, yeah. Okay, so I now want to, so Fagan and Odesky define a line bundle on e to the g. And by this I mean the g-fold product of copies of E with itself. And I'm going to write it down, the definition. Okay, so L here is just going to be a degree 1 line bundle on E. So let me write down. So what I mean here is take the tensor power, the n first tensor power of L, that's sitting on, see, I've got all these E's, right? E cross E. And I sort of think of them as ordered in the same way as these things. And I take this line bundle of degree n1 on here, line bundle of degree ng on here, and I take the external tensor product of those to get myself a line bundle on this thing here. But this isn't quite what we need. We now need the Poincare bundle on E cross E, diagonal minus 0 cross E minus E cross 0. This line bundle here. And what are we going to do with it? Okay, so here's a proposition. Global sections of this on E to the G is always n. Now, one thing one has to do sometimes is, this point of view here was saying I can interpret E as inside this projective space. In other words, saying that is that the degree 1 part of the algebra is really this. But because we've got this description also, this is theta functions are sections of line bundles on elliptic curves. So this thing here is really the global sections of this line bundle on E. Sometimes you have to change your point of view and think of the degree 1 part of Q as being sections of this line bundle on E to the G. So both things are useful. This is what's called an ample line bundle and generated by its global sections. And thirdly, this is very ample if all the ni's are greater than or equal to 3. And let me just, a cute thing, okay? When you learn about continued fractions, one of the lovely events is, that you encounter is that this thing here is a ratio of 2 adjacent Fibonacci numbers. 2 adjacent Fibonacci numbers. Well, if I take these negative continued fractions, it's also a ratio of 2 Fibonacci numbers, but they differ by 2, depending on, yeah, right. So the first one you get is 3, which is 3 over 1. The next you get is 3 plus, 3 minus a third, which is 8 over 3. And here you have 3, 5, 8 in your Fibonacci sequence. Anyway, that's kind of cute, very ample. Okay, now, whatever all these algebraic geometry words mean, they allow you to do this. Okay. Whenever you've got an ample bundle, that is generated by its global sections, nice map. In this case, we'll go from E to the G to the projective space of the dual of this thing here. And it's an embedding. So we get another embedding inside P of this, but now it's of E to the G. And we define the characteristic variety Q in K blah blah is the image of this map, map. And we will denote it by xn over k. Here's a theorem. Xn over k is isomorphic to e to the g if and only if all the ni's are greater than or equal to 3. In general, x the n over k is a quotient of e to the g by some finite group. I'll call it n over k, where sigma n over k is a subgroup of the symmetric group of order g plus 1 factorial. Now, of course, the symmetric group on g letters acts on here in the obvious way. There's a slightly less obvious action of the symmetric group of size 1 bigger on here. And it turns out that this thing is a quotient by something. And what subgroup is it? So you know that this is generated by the simple reflections. What I do is I take this thing here is generated by the simple reflections for which the corresponding ni is 2. Which the corresponding ni is 2. So this thing here is governing quite a bit the structure of this characteristic variety here. You'll notice that this is the same sort of subgroup that always comes up when you're, doing Lie-Therian type AN and, you're taking some parabolic subgroup and you take the Weyl group associated to that parabolic subgroup in which simple reflections do you put in? You put in those simple reflections corresponding to which nodes you omit? No, keep. Which nodes you keep? No, oh, I can't remember, but not serious. Okay, so why is this characteristic variety important? So Natalia mentioned that there are things called point modules, and this every point on this characteristic variety determines a point module. I have time to say anything about these, but point modules are sort of, for graded rings, what one-dimensional modules are for ungraded rings. Or if you want to think more from a geometric perspective, which is quite good, non-commutative algebra will see certain geometric things and not other geometric things. Sort of like, in symplectic geometry, you see certain kinds of subvarieties of a symplectic manifold, but not others. These kinds of graded algebras, they see certain geometric objects in Pn minus 1, but not others. These are the points that it sees. See, I've got this xn over k, the image of this, inside the projective space of the dual of the degree 1 part of the algebra. And the algebra is only seeing a certain part of this full projective space in some sense. These are the points. Now, there exists a surjective map from Qn over k, something, I'll just write it down. It's really OP restricted to x n over k. No. Okay. So this is something called a twisted homogeneous coordinate ring. So these things were invented by Arten, Tate, Vandenberg, and independently by Fagan and Dodesky. This algebra is a graded algebra. It's trying to be the homogeneous coordinate ring of this thing, except it's not commutative. However, there is a category of this. You take the graded modules for this, and you mod out by something some category of modules that you're not interested in. This thing here is equivalent to the category of quasi-coherent sheaves on this, right? So here we have this non-commutative algebra. It maps onto this thing here. This is not commutative, but it's as good as commutative from point of view of representation theory. So we understand all the modules of this. So we understand a big chunk of this. And I think I better stop there.
So earlier in your talk, you stated a conjecture about this algebra Q and it has a lot of variables, Q and K,
yep.
eta, theta, eta, tau, and you said it's finitely generated over its center?
It's finitely generated as a module over its center, if and only if this point on the elliptic curve has finite order.
Yes, that's the statement that you wrote
yes.
down. And
yes.
I'm just wondering first, whether there have been cases, which I'm inclined to believe there are, that have been verified?
Oh, absolutely, yes. If K is 1, then it was verified by Tate and Vandenberg. And I said that one direction we can always prove, and that's really a consequence of this result here. If this is finite over its center, this would have to be finite over its center. And the only way this can be finite over its center is if this has finite order on that, and that's sufficient to get the finite order of something else.
So the side that it states about the point being rational is easy to imply that the algebra is finite over its center, finitely generated over its center? Because you said one side is relatively clear, and I don't understand which side is supposed to be clear.
Oh, that if it's finite over its center, then the point has to be a torsion point. Yes.
So that part is what you can always verify.
Correct. Correct.
And the other side, starting from a point which is rational, then you said if K is 1, it has been verified for, okay.
It's very hard to compute the center of these things. And Tate and Vandenberg's result for K equals 1 goes by reduction to a finite field. They reduce to doing something over a finite field. Yep.
Yeah, I have a sort of a philosophical question. Why is it sensible to take an algebra defined by relations which are given by a solution of the Yang-Baxter equation? What's the meaning of the Yang-Baxter equation here?
Probably better at answering that question than me. Why should the Yang-Baxter equation be so have such an important impact? Gosh, from the point of view of algebra, I don't have a good answer for that. I'm sorry.
Yeah, no, I'm not sure how it happens. The way...
No, I don't think that's it. No,
it's not. You're right. No. It's different definitions. So,
no, it's.
So the question is why can I take another R? Why should I take this?
Well, I think if you take an R at random, then the algebra you get defining it in this way will be very small, maybe finite dimensional. It's like sort of picking relations at random, I think.
Yeah, okay, so it's like closer to be a polynomial, closer to be a deformation of the polynomial algebra thanks to the Yang-Baxter equation, more or less.
Yeah. I don't know. I'm sorry.
Okay, right. Thank you, Paul.
Okay, thank you.
The coffee break will resume at 1:10 past.